Okay, let's get started with class for today. So some admin things before we get going with actual stuff. First thing is that assignment 1 is live. By the end of this lecture, you'll have seen all the math you need to understand in order to do assignment 1. So if you want to find it, go to your Canvas page, just like this, go to assignments over here, click on assignment 1, and then I will not click on the solutions, but they do exist, but you can click on the problem set, and this will give you the problems that you are asked to do. There's a mix of problems, some MATLAB stuff, some pen and paper stuff. Give it a try. Second thing to do in terms of admin is the add drop deadline is this Friday. So basically with this course, if you want to be able to, if you're thinking this isn't for you and you want to drop it, if you do it before this Friday, it is very easy. You just click a few buttons and it happens. If you are trying to drop the course after this Friday, it becomes considerably more complex. You have to fill out paperwork and go talk to several different people on campus, and it's quite difficult and not guaranteed, but we have friends that work in the advising office that really help to get people through that process, but it can be a little muckier. So if you do know this course is not right for you, the right time to drop it is now. After this add drop deadline, nominally the only way you get to drop a course is if there's exigent circumstances. So like there's a tragedy in the family, or something comes up you're not aware of, or you break your arm, or something that explains why you wouldn't be able to continue your academic workload. So if you want to do that easily and you know you want to drop the course, please do it by this Friday. We'll be sad to not have you here. But then again, if you drop the course, you can still come here. I won't say anything. It's fine. And then finally, last thing to mention is Peter sent out some announcements. You can always find the announcements here. You also get them in email form, talking about class reps and how that's going to work. Read those instructions. In practice, class reps for this course don't do too much. A lot of the class rep process has on-campus meetings you go to, and you all can't do that because you're at your home schools during the middle of the day, which is when they do all the meetings. But you can send in feedback, and it is a way to be a voice for other students around you in case you don't feel comfortable raising. If there are people in the room that don't feel comfortable raising concerns with us directly, you go through your class rep, which then comes to us. It's a good safety process. It's a thing that makes courses in general work pretty well. For Maths 199, the amount of times a class rep has had information for me across 6 years of teaching the course was 0. It just doesn't come up. But don't let that stop you. It's a cool thing you can put on your resume next to everything else, so go for it. And then I think that's it for the admin. Before I start doing a bunch of math at you all, do you have any questions for me? No? 5, 4. Oh, I haven't explained this yet. Math questions are awkward. If you slowly count backwards, sometimes people feel compelled to ask a question to fill the awkward silence. Yeah.
Do you have the answer for last week's for the line problem?
Yes, I do. I won't go through it now because it'll take more time than we've got, but do you want to just know the punchline of when you can escape and when you can't?
Sure.
You can escape from triangles, squares, and pentagons, but not hexagons or higher. If you want to know how, talk to me during the breaks or put a post on Ed and I'll describe an explicit process for this. Several people were super close to the way you do this when we were talking last time. The process of using the fact that you don't know any fear is quite important. Cool. Anything else before you get started? No. Cool. Awesome. Math time. Time for math. Okay. So I've said today we're going to talk about how to add. Just to be very clear, I am not talking about 1 plus 2 is equal to 3. Instead, I want to talk about things called series. In other words, what happens when you add something up a ton of times? You have 1 plus 2 plus 3 plus 4 plus 5, ... or 1 plus 1 plus 1 plus 1 off to infinity, or 0 plus 0 plus 0 plus 0 plus 0 off to infinity, or 1/10 plus 1/100th plus 1,000th plus 1/10,000th off to infinity, or 1 minus 1 plus 1 minus 1 plus 1 minus 1 off to infinity. I'm talking about infinite sums, how to add infinitely many things together. And so I claim that you know the answers to all of these things here. If I add up a bunch of ones off to infinity, what do I get? Infinity, thank you. We should denote positive infinity, because if I had like minus 1, minus 1, minus 1, minus 1, minus 1, I might want to say that's going somewhere different, so I could write negative infinity. If I add 1, 2, 3, 4, 5, where do I go? Same place. These are going to the same sort of asymptotic value of going off to infinity. This one is maybe growing there faster in the sense if you look at sort of what happens along the way, but the thing they get to in the end is ultimately the same. If I add a bunch of zeros together, do I go to infinity? No. Common mistake people make in this kind of a course is they assume if I add infinitely many things, I must get infinity. No, that's not true. You can add infinitely many things and you can get a finite value, like 0. Or how about this one? If I add a 10th, a 100th, a 1,000th, 10,000th, what number do I get? 0.1 repeating, also known as 1/9, right? Cool. And if I add 1 minus 1 plus 1 minus 1 plus 1 minus 1, where does that go? Does it go anywhere? No. So this is something we're going to say DNE, which will be shorthand for does not exist. And we'll be making that a bit more rigorous throughout this talk. But the idea is when I add these values here, I start with 1, subtract 1 and get to 0. I add 1 and go back up to 1. I subtract 1 and go down to 0. It keeps oscillating back and forth between 1 and 0. It's not settling down to a value. So we say it does not have a limit. I want limits to be single values that things have. Cool. This kind of okay so far? If anything today feels a little hand-wavy, the answer is that behind the scenes, subtly, it is. If you want to do all of this extremely painfully rigorously, one, talk to me. I will give you resources. I can happily do this all with you. You wind up going through, has anyone heard of the Greek letters epsilon and delta in the context of limits? Yeah. So that will connect in with this at a more rigorous level. If you want to know how to do that, let me know. If you're into calculus and you want some books to read through that, I can give you references. Michael Spivak's calculus is one of the best pieces of mathematical writing out there. But for today, we are going to be mathematical engineers. We're going to do proofs, but we're also going to have some vibes in our proofs. And to start with that, I need to give you a definition. When I talk about these infinite sums, I want a word for those things. A series is an infinite sum like the ones we're doing above. And the notation we got for these things looks like the following. And a big capital sigma looks like this E that someone sort of mangled a bit and chopped off bits from. I'm going to put down here this n is 1, up here this infinity. We're going to f of n. This notation means in total, f is going to be some function. So f could be n squared, or f could be sine of n, or f could be the first prime that's smaller than, or the largest prime that's smaller than, or f could be just 2 every time, doesn't care about what n is. It's some function, it's a rule, it exists in the world. If you know what f is, when I write down this, write this sigma notation, this sum from 1 to infinity, that just means sum up values of f one at a time, starting at 1, and add them all up. Go off to infinity. Talk about the limit. And then, if you don't want to go all the way off to infinity, you can talk about the partial sum. And so that's what happens when you add them all the way up and you stop at some value n. This okay? Cool. And now, I was talking about these things going to infinity, or going to 0, or going to 1/9, or not existing. So there's some fancy words for going, because going doesn't sound very mathematical. It is, but we like using slightly fancier words. I'm going to say that a series converges if its partial sums converge to a single fixed finite value as the n in the top of the partial sum goes to infinity. The opposite of converges is diverges. So that's the opposite. If you don't converge, you diverge. You go somewhere else. And a specific kind of divergence, if your sums say partial grow without bound, you would say you're diverging to positive infinity. All we're doing today is exploring these definitions and working through how do you write proofs and arguments that show things that do this stuff. So this is the wall of text for the day. Beyond this, we're working with these ideas, exploring them, and trying to figure out how they go. Which is a way of saying these words are very important. Do these words make sense? We're going to talk about them. We'll do examples with them. But people okay with this at a surface level right now? 5, 4, 3, 2, 1. Excellent. Cool. By the way, a valid question can be, can you pause for a second so I can keep up with my writing? That is a legitimate thing to ask for. Just mention that. Okay, so we've got series, ways to sum a bunch of things together. We've got the idea of what happens for them to converge, so go to some finite value, or diverge, so not converge. And a particular kind of divergence that happens a lot is blowing up to infinity. So let's look at some. We sort of analyzed these things up here before. So like diverge, 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 converge, converge. These ones diverge to plus or minus infinity. This one didn't even diverge to plus or minus infinity. It just did not converge, diverged. So what I wanted to start off today is looking at some slightly weirder sums. So what are some more esoteric series we want to look at? So the first one has a name. This is called the, has anyone seen this before? Know its name? This is called the harmonic series. And this is basically saying, what happens if I, add 1 plus a half plus a third plus fourth plus fifth plus dot, dot, dot. What does this do? It's kind of the first interesting series you expect to do. Like if you add 1, 1, 1, 1, 1, that's clearly going to go off to infinity, right? And if you add 0, 0, 0, 0, 0, you're going to go to 0. This thing right here is kind of in between. You're adding infinitely many terms. They are, however, getting smaller along the way. Does that mean that it's going to have to settle down to some finite value? Sort of like we saw here with the 10th, 100,000 thing? Go to some fraction? Or is this still going to be something that blows up? Because I am adding infinitely many things. And they are certainly bigger than tenths, hundredths, thousands. They're much larger. So it's interesting. It's not clear what happens. Second series I'll mention, because it shows off an indexing thing I can do here. You don't have to start at 1 every time. I'm starting at 0. Shocking. I'm going to add up 1 over 2 to the n. So I'm going to add up all of the non-positive powers of 2. So 1 plus half plus a fourth plus eighth, so on and so forth. Any number to the 0, by the way, 1. Any non-zero number. Don't talk about 0 to 0. These are two different series. You could say, like, this one again, I'm subbing infinitely many things. Doesn't mean it blows up. They're getting smaller over time. Does that mean it's going to converge? How would you study something like this? If you want to study what these series would do, what is the first sort of exploratory thing you would try? Substituting in what sense? Yeah. So the way you try this, because like I cannot, in one sense, like we can't try it in the sense like I can't add up infinitely many things in my head. My brain does not hold infinite storage space. But a reasonable thing to do, if you want to figure this out, is make a table of partial sums. So this right here. Because a reasonable thing to think about for what trying it might mean is, well, we can't add it up to infinity, but what if we just start adding it up to n is 1, 2, 3, 4 along the way, and see what we get there. So let's try it. Let's see what comes out. So if n is 1, and I'm doing the 1 over n's, what do I get? What's the first partial sum here? 1. What's the next one? 1 plus a half, so 3 halves. What's the next one? 1 plus half plus a third. It's messy fraction time. I'm just going to give you these ones. 11/6, 25/16. You can check my math if you want. You start summing these things up. Is it clear what's happening at these first 4 values? No. 4 is not a whole lot. If I had more time, I would do this out to like 12. Do you want a spoiler alert of what happens when you look at 12 more values? It still isn't clear. You're not going to get a pattern here. But let's try doing powers of 2. So when n is 1, what do I get here? Slightly trick question. So I'm starting at 0 and I'm going to 1. Yeah. This is sneaky. And really you could say like this is a crap table, why'd you draw it this way? But if you're going from 0 to 1, you've got 2 terms to start off. So 3 over 2. They have a term in common. They're clearly the same. That's not true. N equals 2. What's the next one? 7 over 4. That's right. Next one. That's right. So the next one you're going to get is going to be these ones. And I heard a 15/8. What's the next one that comes after that? Yeah. Is there a pattern you're seeing here? Yeah. So these look like there's a conjecture you can make here. Guess the pattern is for going from n equals 0 up to n, 1 over 2 to the n. We are saying, so 1 gave you 3 halves, 2 gave me 7/4, 3 gave me 15/8, 4 gave me 31/16. what is the denominator in each one of these? It's power of 2, and what is that power of 2? If you're guessing from the table. Yeah. And what is the numerator? 3, 7, 15, 31. That's right. Cool. Now, is this a proof? No. We just found a pattern and saw it worked for 4 examples. That's not a proof. We haven't proven this yet. But it is useful if you don't know how to write a proof. Like, if you're investigating this for the first time, you need to come up with a guess before you can write a proof. This is the first step of doing this mathematical problem. Whereas for this one, this plotting exercise did not help us at all, right? We could do more things if you wanted. I claim it is just going to stay messy. So what I want to do right now is, I want to do a lot of things. But the first thing I want to do is I want to show you how you might rigorously show this. The proof method we're going to do here is something we don't expect you to fully internalize. For those of you who've ran into proof methods before, this is a proof by induction. Induction is, if you're going to be formal with it, spicy. But intuitively, it's actually not hard. People make it seem scary, and they make it seem very formal and structured, and it's really not. It's basically the only possible thing you could do if you want to prove something about an infinite set. But I do want to do it for you here, because it's a class where we prove things, and I think it's really neat. And if you are going into fields like anything touching computer science or mathematics, you will have to do a lot of this. So I'm going to claim the pattern that I did up here. And I claim that that pattern holds. And I'm going to do the proof in 2 steps. So first, we notice that we've shown this pattern holds for some small values of n, so 1, 2, 3, and 4. And that's sort of a good start. We went up here, made this table, saw the pattern holds for small values of n. Now, the next thing we're going to do, show it's true for every number n, is the following. I'm going to show that if it holds for some n, it will continue to hold at the next n, n plus 1. What's the result of this? If you know something is true for, say, 1, 2, 3, and 4, some small values, and you know if it's true for n, it's true for n plus 1, what's going to happen? Well, it's true for 1. If it's true for 1, it's true for 2. It's true for 2, it's true for 3. It's true for 3, it's true for 4. It's true for 4, it's true for 5. So on and so forth, off to infinity. It is always true. The visual in your head should be knocking over dominoes. Step 1 is knocking over the first domino. Step 2 is ensuring all your dominoes are lined up. Consequence, all the dominoes fall over. In other words, your claim is always true. I haven't done this yet. Yeah. I need to do this. So this is the will. Yeah. And I should note this is true for all n in the natural numbers. Natural numbers are your counting numbers. 1, 2, 3, 4, off to infinity. This is not a good proof technique if you're trying to prove something is true about all the real numbers. Why couldn't you do this for real numbers? Which thing would you find it hard to do for real numbers? Can you tell me what the smallest real number is? -1. Like, there is no smallest real number. But I like that. 0 is the smallest real number in some sense, metrics. But if even you could find a smallest real number, can you line up all the real numbers in a row? Can you show that if it's true for some real number, it's true for the next real number? The answer is no. It is no intuitively. It is also no when you start taking a bunch of logic classes learning about cardinality of numbers. That second thing is spicier. But this is a technique for now. This holds only for numbers you can count in a nice sequence, so the natural numbers. So I need to actually do that showing thing. And the way I do this is as follows. I'm assuming it's true for some n. So I'm assuming it's holding at some value n. And so I get to assume that our formula we came up with is holding somewhere. 1, 2, 3, and 4 is what we've got so far. What can I do with that? Well, we want this to be true for the next value, right? So I want my formula to work when I'm looking at the n plus 1. But what can I do with the n plus 1 case? Well, whenever you don't know what to do in a math thing, expand stuff. And whenever you're thinking about how to expand things, try to expand it in a way that's related to what came before. The sum of this thing up to n plus 1 is the sum all the way up to n plus the n plus 1th term, right? If I'm going all the way to n plus 1, it's the same as going all the way to n and then taking one more step. People okay with this? And what do I get to know about this? What's the thing that I've shown for some starting value then? I've got this formula. I know my claim is true up to 1, 2, 3, and 4, and I'm trying to show it's going to hold at 5. And so what I'm going to do, I'm adding the stuff up, I'm going to use my prior work. I know my sum is true up to 1, 2, 3, 4. I want to show it's true at the next one. And now I've just got fractions. I'm going to combine denominators. If I want to make this into n plus 1s, I'm going to multiply everything at the top by 2. And then I got minus 2 plus 1, so I can simplify this down to 2 to the n plus 2 minus 1 over 2 to the n plus 1. And in total, what is that? I've shown that when I add all the numbers up to n plus 1, I get our formula where the n's have all increased. So in other words, I've shown our claim is true at n plus 1.
What operation did you do to make the formula in brackets to the one below? Like,
So here to here?
no, there to below.
There to there. Multiply top and bottom by 2. So 2 to the n goes 2 to the n plus 1. Minus 1 goes to minus 2. 2 to the n plus 1, 2 to the n plus 2.
I'll multiply by itself.
Yeah, yeah.
Yeah, sorry.
Because I wanted to get common denominators so I could combine the fractions. Cool. And I claim to you that I have now proven our result. Because what did we do? Well, at the start, we showed our claim is true at 1, 2, 3, 4. We did some examples. We saw, hey, pattern holds. And what did I do with that? Well, I said if it's true at 1, 2, 3, 4, Then what happened at 5? Well, 5 is just sum all the way up to 4 plus another 1. I know the formula is true for 4. Add another 1. Now it's true at 5. Now I know my claim is true for 1, 2, 3, 4, 5. Well, 6 is just 5 and 1. Plug in the formula, add another 1. Now it's true through 1 through 6. Repeat the process. Again, again, again. You just keep doing this, and you wind up with something that is true at all values of n. Congratulations, you have seen your first induction proof. We're not expecting you in most contexts in this class to reproduce this. This is not the kind of thing we're going to throw at you at a test or exam. It is spicier than the median thing. But on the other hand, it's also not that spicy. This is a thing you can follow along with. It's a cool technique, and it's the kind of math that you get to do when you actually are working in this rigorous context and writing proofs. Questions here? I'm sensing like sort of stunned confusion. I'm going to pause for like 2 minutes, talk to the person next to you, and express your stunned confusion to each other. Go. Yeah. No, this is a geometric series. Harmonic series we haven't touched yet. That's the one I've read, yeah. Okay, let's bring it back real quick. Any questions that have came out of that? People maybe a little happier or a little more united? Okay, cool. So, like I said, not the kind of technique we're going to expect you to reproduce too often. If you find yourself in the assignment writing a proof by induction, you're probably overcomplicating it. But give it a try. It's fun. It's cool. The main thing you're going to be using when you're in the assignment, however, is a different technique. And in mathematics in general, I claim to you that there are really two series techniques. So spiritually speaking, there are really two ways you prove things about series anywhere in mathematics. One of them is what we just did. Find a pattern. And the second, which is much more straightforward and you can abuse so thoroughly, everything falls to this test. Is you can compare something that you know, or something you're trying to figure something out, to something you already know. So you either find a pattern or compare it to something else you've already studied. This sounds kind of dumb, but as you'll see, especially in the second half of today, this is an astoundingly powerful technique. And what does the comparison test say? It says if the sum of some series. And I'm going to note this a sub n. This is another way of writing things. You don't have to have it like in function form, f of n. You could also just have a sub n to say like it's a sequence of numbers. I don't have to tell you what the rule is. Like here's just, I'm going to write them out for you. I'm saying this n is 1. You could do this n is 0. Just make sure they start at the same place. Are both series. And all of the terms are not negative, because you can get around to some serious shenanigans with negative numbers. And the ANs are less than the BNs for all natural numbers n. Then, two things follow from this. Suppose the ANs diverge off to positive infinity. What has to happen? If we've got these ANs and these BNs, the ANs are less than the BNs, the ANs go off to infinity, what has to follow from that? Yeah. The bigger ones also have to go off to infinity. Like, it's pretty straightforward, right? Slightly more surprisingly, but not too differently. Suppose the BNs do not go off to infinity. So not case 1, now we're in a different case, case 2. Then what has to happen? If the BNs are going to converge, they're going to settle down some nice limit. What do you think the ANs have to do? Can they fly off to infinity? No. And it turns out that they can't also do anything else like that either. They can't do like that 1, 0, 1, 0 oscillating thing. They also just have to straight up converge. And the reason for that is the terms are positive, and so you can't oscillate if all your terms are positive. You're only going up as you add terms. This is a pretty straightforward test. It is just like, if you give me a series, if I can make something smaller than it that blows up, then your series has to blow up. Make something bigger than it that converges, then your main thing's got to converge. It's not too complex. It's really powerful and does a lot of stuff. And second half of today is where we're going to use a lot of this. We've got about 10-ish minutes before we go to the lab, though. So I think what I probably should do is a bit of MATLAB. Do you want to see one example of this first, though? OK, I'll do a quick example of this. And then we'll do some quick MATLAB. And then second half of the class, we'll do some spicier examples of this. But to do a quick example of this, I'm going to turn to that harmonic series. And I claim this diverges. This goes off to positive infinity. And the reason why is pretty cool. So if we write the series out, I get 1 over 1, and then 1 over 2, 1 over 3, 1 over 4, and 1 over 5, 1 over 6, 1 over 7, 1 over 8, 1 over 9, 1 over 10, 1 over 11, 12, 13, 14, 15, 1 over 16, 1 over 17, 1 over 32, and keep going. This is just what the series is, right? Like, I'm just writing out terms, haven't done anything. Now, what I'd like you to do here is we're going to do a bit of a comparison here. So I'm going to think of this term, this series right here. This is going to be my BNs in the comparison test. In other words, I'm going to have Bn is 1 over n. Now I'm going to show you something that's smaller than it that's going to blow up. It's going to go off to infinity. And I'm going to do it as follows. So 1, half, a fourth, and a fourth, an eighth, and an eighth, and an eighth, and an eighth, and a 16th, and a 16th, 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 32nd, and 32nd, so on and so forth. You can't quite see what I'm doing here. I took this third, and I made it smaller. It's a quarter. Oops. I took the 5th, 6th, and 7ths, and I made them all 8ths. I took 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16ths, and I made them all 16ths. 17 32seconds. Those all just became 30seconds. So I have made all my terms either the same or smaller. So these are my AN terms in the comparison test. This is going to be the thing that I'm going to wedge beneath it to make it blow up to infinity. And what is the thing that happens with these? Well, what's a quarter plus a quarter? What's an eighth, an eighth, an eighth, and an eighth? What is 8/16ths? I've got 8 of those. Yeah, I've got 16 32seconds. That's positive infinity. Bam. It's really slick. This proof is nice. So this is comparison test. This is what we're doing here. If I was writing up formally to put this on an assignment, if I was submitting this as my own work, I would have a few more words here, but morally speaking, this is what goes in this. This is what goes into valid proof of this kind of claim. Questions here? People okay with this? Cool. Give it some thought. Think about it. We'll do more examples comparison test second half of the class. We're going to do a bunch of weird nuanced things with this. But this is what a lot of comparison test things work like. You look at your series, you say to yourself, this has to blow up. And you just try to find something clever to wedge underneath it. And the way you find the clever thing is, honestly, you spend a lot of time doing math, and you watch people do stuff like this, and you just come up with an ever-growing bag of tricks you can deploy on your own for the next problem. If this is the first time seeing this, you would almost surely not think of this pattern on your own. The point of taking classes at university is to learn these patterns. This one is really neat. You'll see this use of powers of 2. We keep doing this in this class. Powers of 2 show up everywhere. If you can find a way of relating whatever you're doing to powers of 2 in some clever way, you've almost certainly made the problem simpler because humans are much better with 2s than they are with other numbers. Anyways, cool with this? Okay. Let's go and do a bit of MATLAB then. Yes?
What's that technique called?
This technique right here? This is comparison test. Like in terms of this bit. In terms of finding the lower bound that's got all the powers of 2, I think it's just like being clever. And being clever is really do enough math where you recognize the patterns. It's pattern matching. Cool. Okay, we've got 7 minutes. So a little bit of time for me to show you a bit of MATLAB. I might go over a little bit just so we can get the MATLAB done so that the lab feels okay. So, guest device. Bop, bop, bop. Cool. Okay, so behind everything we've just been doing is this implicit idea that you can quickly calculate a lot of partial sums in order to find patterns or find lower bounds on them in some way. And a thing I did with you when we were doing all this is I just kind of noped out of the 1 over n thing real quick when we were doing the partial sums. I was like, yeah, we'll do it up to 2 or 3, and then I don't want to do any more of this. That's because that's profoundly tedious. It's quite difficult. It's annoying. Whenever in life you find yourself with a tedious, annoying task, make the thinking rock do it. Make your computer solve the problem for you. Do not do it yourself. So what I want to do for you now is show you a trick to have computers sum up tons of things for you, and it is the humble for loop. What I'm doing right here is I've made a script. If you're following along and doing this yourself, you go to New Script. A script is literally just what it sounds like. You can think of the computer as looking at what I'm about to write down here. Oh my god. Copilot, cursed. Why? Go away. Sorry. Copilot will just do this. It'll come up with ideas of what you want to do. It's always wrote the word sum and is like, here's some sums for you. A script is just a list of things that the computer will do in the sequence you write them down. So if I want to do a script that calculates sums for us, I specifically wanted to calculate partial sums for the harmonic series. What could I do? Well, I like to use very verbose variable names. You don't have to do this. Oh, please don't do that. That's wrong. So I'm going to make a variable. This is going to store my partial sums. I'm going to start off at 0. And I'm going to type something like 4n is equal to 1 to, what partial sum do you want? 100. You take this, and I'm going to add to it 1 over n. And I'll type an end. What does this do? It does what it looks like. It tells the computer to do the stuff inside this for end block 100 times. And it tells it to make n increase by 1 each time. Cool. I wrote a script. If we hit run, what happens below? Well, first it's going to ask me to save the thing. For scripts, the name you give this does not matter. And then what it does is exactly what I told it to do. It made the 0, summed all these things up to 1 through n, it displayed them at the end. Does anyone know why I've got the semicolons here? What happens if I get rid of those? Yeah. Whenever you want to know what happens if you do blah, if you're in a programming language, just do it. If you go down here and look at what happened when I got rid of that semicolon, it's like printed out in a billion different things, right? What it's doing right here, when you're done with a semicolon, it says, whenever you're done with this calculation, print what happened. So if you get rid of the semicolon, you see all the partial sums on the way to your final answer. You should be aware that printing a value does not mean the value is saved. So do not rely on that to do anything. In general, it's probably good form to have semicolons at the end of every line. And then if you really want to see something, use the display command. If I use a semicolon there, I don't get the, so I didn't have that before, it's the same thing. Disk just automatically prints no matter what you've got. Does this kind of make sense? It's really not too wild. It does what you think it does. A second thing I want to show you, just to finish up all the stuff, actually, let me do that more slowly. This was a script. It was a set of rules for MATLAB to do one by one. You don't always want a script. Sometimes you want something that's like a function you can call down at the command line. So sine of 10, sine's a function. You plug in 10, you get a number that comes out. You can make your own functions in MATLAB. This is the power programming. It doesn't matter whether you pick script or function, but you might as well pick function because it'll give you a format of what functions look like in MATLAB. We're going to get rid of all of this. When you define a function in MATLAB, there's a few fussy things you have to do that are counterintuitive and that will create, I think, 90% of the coding problems people have in this class at the start. When you have your function, the first thing you have to do is you have to have function, the output, or in this case, multiple outputs. I'm going to name it partial sum. I'm going to name this partial sum calculator, harmonic. I'm going to put n here. Here, n is the input, and partial sum is the answer or the output. You don't have return statements if you're used to something like Python. It's all done up here at the exact start. And then from this, you can use the exact same process we did before. So partial sum is equal to 0. And then I'm going to go all the way to capital N, because now I don't have to fix the value. Before I had to say like 100 each time. This one I can just type in. I'm going to make it a function. The function can take in any input we want. And what should I write here? What goes here? Well, partial sum is going to be equal to, I want to take the partial sum, whatever it currently is. I want to add on the next term. Throw a semicolon here, semicolon here. Don't put semicolons at the end of your for statements or stuff like this. Semicolons come at the end of not function or for or if statements. And this should be the exact same thing we did before, but now it's sort of in function form. Now, like I said, the most common issue you're going to run into when you do this, when you hit save, you desperately, desperately need to make sure that this function name right here, the title of the function, matches the title of the function you've got yourself. And MATLAB is helpfully hiding the function from me. But this has to be an exact match for what you've done here. If it's off, even by a capital letter, it will not work, and it'll be so annoying. You also cannot define multiple functions that are callable from the command line in one file. You only get one function per file. It's a choice. I don't love it, but that's okay. But once you've done this, then you've got something down here you can call. And you get the exact same answers before, and you can call it for sort of any value all at once. We're going to do a lot of practice with this, but these are the fundamentals of how to do this partial sum stuff and how to work with series, that kind of thing. People okay with this? Cool. Okay. It is 17:23. Be at the labs at 17:33. So we've got 10 minutes to get over there. If you brought some food, also have a snack. Make sure to bring everything with you. This room is not secure, so do not leave laptops or anything that you don't want to have potentially get taken away. If you want help walking back over to the labs, I'll be going over there in a few minutes myself. We are right on time. Okay, time for part 3 of class. Every lecture of Max is a marathon. This is no exception today. So hopefully lab was a helpful experience. I did not expect most people to get through the entire lab. I didn't expect hardly anyone to do that. But if you got through problem 1, you're in a good space. If you didn't get through problem 1, try to do that. And if you get stuck on it, email me, email Peter, contact us on Ed. We can set up Zoom things with people to help you get through this. The biggest initial difficulty that about a quarter of people have with Max is if you haven't done much coding, the coding comes at you pretty quick. That does not mean that you cannot do this, but it does mean that your first few weeks of Max are harder than other people's first few weeks of Max. But that also means that you shouldn't feel bad about asking for help to get up to speed and to get more comfortable with stuff. So if that is you, please reach out. We're happy to help. But for right now, what I want to do is get into some comparisons test stuff, because this is sort of the first half of the class is basically what are series, how do they work, how do you find these patterns kind of thing. The comparison test is really 90% of what you actually use to analyze series. Basically, if you compare it to something else, you can figure out if it converges or diverges. It works a lot of the time. If you throw in series for the assignments into a lim, it'll probably start giving you lots of wild tests. It'll be like, use the p test and use the integral test and use blah, 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 blah. There are a bunch of fancy tests out there for dealing with series. They are all the comparison test in a variety of different trench coats. The comparison test gives you every single other one of those series as long as you can be creative with what you compare to. And so that's why I want to focus on it here, because if you understand this, you really understand everything that's going to happen with this. And so if you go on to later courses in calculus or analysis, you are going to be in a good position. So let's do some examples with this. We did the harmonic series earlier. I want to do some more examples with this. So what can we do? What's the fun one? Yeah, let's do the weird one first. This one's fun. I'm going to do something a little hideous with notation here, but it's legit, trust me. I'm going to do the following sum, and it's going to be of things that look like the harmonic series. But I'm going to do something a little different. As opposed to saying n is 1 up to infinity, I'm going to give you a different rule. I'm going to say, give me all the natural numbers that don't have 9s in their digits. And so I'm just going to write down that rule in the subscript on the sum thing. And I want to look at that sum. So this looks like the harmonic series. You get 1 plus a half, plus a third, plus a fourth, plus a fifth, plus 6, plus 7th, plus an 8th. But I'm not going to have the 9 term here. The 9 term is going to be something I remove. And similarly, when I get to 1 over 19, I'm going to ditch that one as well. And same for 1 over 29, 1 over 39, 1 over 49, dot, dot, dot. And when I get to 90, 91, 92, I'm going to get rid of all of those things. There won't be any 1 over 90, 1 over 91, 1 over 92. But other than that, I've got all the 1 over n terms. I'm going to sum them all up. And I'm going to claim that this thing right here, that looks like it's almost all the harmonic terms, right? And summing up all the harmonic terms, that went to infinity. When I sum up all the harmonic terms, except I get rid of the ones with 9s in them, this is no longer going to diverge. It's going to converge. And it's converged to something that's less than 80. So the difference between infinity and less than 80 is whether or not you are adding the 9s in their digits terms, which is weird. This is really weird. It's one of my favorite results. People okay with the claim I've written? Not why it's true, but does the thing I've said out loud make sense? Sound okay? Cool. So I claim to you the proof of this is not too bad, and it goes by comparison, or a comparison test. And it kind of does a comparison test similar to how we dealt with the harmonic series. So let me show you how you do this. If I take this series right here, I'm going to write out its terms again. And I'm going to group them like this. These are all the single-digit things, right? 1 over 1, 1 over 2, 1 over 3, no 1 over 9. 1 over 10, all the way up to 1 over 88, but I don't have the terms with 9s in them, so there's no 1 over 19 in here. And the smallest 3-digit number is 100. What's the largest 3-digit number you can make with no 9s? 88. And so on and so forth. Whenever you don't know how to approach a problem, start trying to figure out what it looks like. So this is me just trying to write out the terms here. And another good technique when you're trying to deal with a problem is try to group things in ways that look like they might be reasonable. So if I'm talking about digits, I maybe want to group things by numbers of digits. It makes sense. It's not an unreasonable thing to try. If you're solving this problem on your own, this would be a thing that would probably take you a long time to get to. I know the answer, and so that's why I'm doing this quickly. But the idea of how you get to the answer if you didn't know it is, we don't know what's going on. Let's write out some terms. Digits matter. Let's group them by digits. Take the information you've got, assemble it, try to get to an interesting conclusion. Now, you have seen exactly one trick for dealing with comparison. And it's when you had things grouped, you replace them by the smallest thing in the group. If all you have is a hammer, use the hammer. That's the only thing you've got. So I'm going to take this, and I'm going to compare this like this. Oh, so whoops. Now, is this useful, thing I'm doing right now?
Yeah, because there are 8 versions of 1 over 8, so it all adds to 1.
True. What am I about to show? I have a thing I want to show converges. Am I going to find something bigger than it that converges or something smaller than it right now? Well, I should find something bigger, but what am I actually doing right now? Finding something smaller. So is this correct what we've done right now? No. This is an okay thing to do. When you're writing your proof, not every direction you take makes sense. Before, we did a lower bound because you're trying to show something blew up, something diverged. How would you want to change this if you wanted an upper bound? Should I be trying to make things smaller? Or should I try to make things bigger? So do I want to compare to 1 over 8? What do I want to compare to? 1.
Wait, why do you need to make it bigger?
If I want to show this converges, the way I show something converges is I find a bigger thing that converges. If I want to show something diverges, I find a smaller thing that diverges. And so because we know this is supposed to converge, finding a smaller thing doesn't help you. If I want to say, like, hey, this sums up to something finite, I can say, like, telling you there's something smaller that's finite doesn't help you. Summing up all zeros is finite. That doesn't tell you anything about any series. If you want to show this converges, you find a bigger thing on top of it that forces it down. And so we need to slightly change our technique, but not by much. Last time we did lower bounds. This time we're doing upper bounds. So what's an upper bound on all these terms? Yeah. And these will be 1 over 100, so on and so forth. In some ways, this is better. I don't have to figure out how I add up a bunch of 888 fractions. These are cleaner, so it might be even easier. So how many of these terms are there? Hold that for a second. Why is that true? So how would you prove that? So if you want to make an n-digit number, you can think of it as like filling in a sequence of boxes, right? N boxes. How many choices do you have for your first box? 8. Why is it 8? You have 10 digits. Why is there 8 here? What digits can you not use for your first digit?
0, 0.
You can't use 0, and you can't use 9. So 2 possibilities. How many possibilities for the next box? It's 9. You can use 0 now, right? You're allowed 0. You just can't use 0 in your first box if you're trying to make an n-digit number. ... 9. And so if I have 8 choices here and then 9 for all the other ones, how many do I have in total? What do I do if I have a bunch of different choices? How do they combine? They multiply. If you've got 8 choices here and 9 choices here, you have 8 times 9 choices. If you have 8, 9, 9, 9, 9, you got 1, 8, and then n minus 1 nines. So our upper bound from here is what? Well, I've got 8 one-digit numbers plus 8 times 9 1/10s plus 8 times 9 squared, hundreds, plus 8 times 9 cubed, thousands. What is this series going to be? Is there a rule we can write this? What would a rule look like for this series in general? If I wanted to write this out as a sum, what can I write this as? Yeah. So I could have 8. Yeah. Or I can simplify it to 9/10 to the n. So you've got this. People okay with this so far? I took my original series. I found something bigger than it. I just need to tell us why this converges, and then we should be good. Does anyone recognize the series? Anyone who did a bit for more of the lab, maybe?
Could you show the last page just for a second?
Of course.
Thank you.
Cool.
Is it a geometric?
This is a geometric series. So these are a series that exist out in the world. If you take any number between 0 and 1 and you add up powers of it, like we did earlier today, we took 1, a half, a quarter, an eighth. We did this series when a was 1/2. There is a very nice formula for what this is. Does anyone know what this is? Has anyone seen this one before? That is correct. The proof for this is an induction argument. If you take that proof we did for 1/2 and literally just replace the 1/2s with a's, it is the exact same proof. There is no difference between it. It's in the course book, and if you want more details, talk to me. Otherwise, you can take this as sort of like, from on high, this is a thing that is true and is descended onto you. But if you do want to prove it, you look at your 1/2 proof and just replace the 1/2s with a's. You'll get the exact same argument. It'll all go through the exact same. But if you apply that here, what do you get? What does the sum become in the situation? I get 8 times 1 minus 9/10, which is 8 times 1 over 1/10, which is 80. And so this series converges to something less than 80. I think the exact value is around like 27, 28, something like that. You can do it in MATLAB if you want. It's kind of fun. How are people feeling with this? This is such a legit proof. I really like this. Do you think there's anything special about 9 here, by the way? Like if I got rid of all the 2's, does anything change in my argument? No, it's the same bound here. I'm just like counting. The number of things don't use 2, same argument. You can do this kind of argument to do this with anything. Suppose I had all the numbers that don't have a consecutive like 3 and a 4. Do you think you'd also get that that's finite?
Yes.
Yeah, if you think about writing numbers in like base 34, it's the same idea. Like, in some sense, what this tells you is that almost every number has a 9 in its digits, because when you have all the numbers and you sum up the reciprocals, you get infinity. If you ditch the ones that have 9s in the digits, you get something converges less than 80. So the remainder of infinity minus 80 has 9s in its digits, which is weird. This is strange. I'm going to pause here for a second, talk to your neighbors, see if this makes sense to each other, and we'll reconvene in about 2 minutes. But take a moment to process. Think. THM short for theorem. Thank you. Good question. Yeah. Explain this last theorem? So like why it's true or what it means? Okay, so what it means is if I add up like a to the 0 plus a to the 1 plus a to the 2 plus a to the 3 all the way up to infinity, I'll get 1 over 1 minus a. So if I did this for like the thing we did earlier in class, 1 over 2 to the n. So in other words, if I had like 1 plus a half plus a fourth plus so on and so forth, what it's saying is that becomes 1 over 1 minus a half or 2. So if you go off to infinity. And so if you made this 1 over 3 to the n, sorry, then what this is saying is you should get 1 over 1 minus 1/3, 1 2/3, 3 halves. For why it's true, I skipped that because it's a long induction argument. But if you remember that thing we did with 1/2, where we found a pattern in the sums, you can write down an exact pattern for these sums. I think it's in the course book. And then show it holds by induction by saying it was true at like 1 and 2, and I'll assume it's true at this stage, and I'll show it holds for the next one. Does that help? Okay, let's bring it back. Any questions before we go on to another thing? Cool. Okay, so this was a kind of spicy comparison test thing, but I wanted to have something that was similar to what we did before, but like a bit more. There's a second kind of comparison test example I want to give to you that is pretty straightforward once you can think of it in this way, and I think spiritually sets you up for a lot of other uses of comparison test. So I'm going to write something. It's going to be awful. That's okay. Give me functions and numbers. Just shout them out at me randomly. Don't stop. Go.
5, 6, 7.
Give me something that depends on n, please.
Times 0.
It's the meme number. Haha. Okay. I'll divide it by no zeros. This is a hideous-looking series. What does it do? Does this diverge or converge? I claim it's actually super easy. Looks horrible. I claim this is real easy. Converge or diverge? Which one? Let's do vote. Democracy is never wrong, says the... Oh, that's not actually true anymore. But let me believe in it. I'd like that in my heart. Votes for divergence, hands. Votes for convergence, hands. Okay, claim this puppy diverges. Unless I've made a horrible mistake. Let me tell you why. I look at this thing right here, and I see sine of cos of sine of, oh god, I don't want to do this. What is the biggest sine or cosine can ever be? 1. So what is the smallest denominator can be? If I'm looking at this denominator, this thing is, the smallest it can be is 313. The largest it can be is 315. If I'm trying to show it diverges, I want something smaller that still blows up. So what do I want the denominator to be? Do I want it to be big or small? If I want the thing to be big, what do I want this to be? Yeah. Lower bound will mean I want this to be 315, right? Cool. Now, top. I want this to be a lower bound. This cos term, what's this going to be? It's going to be at least 6, right? 5 times 6 times 7 times 67 times 6 times e to the n. That's all at least 1, right? Sure. Math. I don't want to multiply numbers. And if I sum up a bunch of 1 over 315s, what do I get? Sum up an infinite number of any constant term and you get infinity. You add up infinitely many 315s, you get infinity. Fin. Whenever you see expressions that look like this, or whenever you see expressions that look a bit more subtle like this, if you're just trying to determine divergence versus convergence, be pretty ruthless with what you can get away with. I looked at this thing right here, and I saw e to the n times stuff. And I saw e to the n, and I'm like, well, it's at least 1. And that's it. Don't have to do any of the heavy lifting math. This is what convergence feels like a lot of the time. The things we were doing before, that's kind of like spicy convergence tests. We're trying to find clever ways to group terms. A lot of the times it just looks like this. You just take the individual term and you come up with a nice bound on it. How are people feeling with this? This okay? This is an important thing to internalize. Whenever you're giving something that looks deliberately awful, like, just don't deal with it. Find ways to simplify. Mathematics is all about simplifying. Cool. Okay. There are, I think, 2 directions we can go with the last 20 minutes in class. One of them is MATLAB directed, where I could try to show you how you'd write code to actually figure out exactly what this series is. We've showed it was 80, or bounded above by 80, but the actual sum is quite different. It did a lot of bounds here. I could try to write some MATLAB code that shows you how you would add up all the terms where you don't have a 9 in your digits. That's option 1. Option 2 is I can do a very cursed bit of pure mathematics, or I can show you a fun fact about the alternating harmonic series, and in particular prove to you that addition is not commutative, which is very funny. Votes for option 1. Votes for option 2. Okay, awesome. If you want to see the option 1 stuff, flick me an email. I can write the script for you, and I can try to record myself while I do it so you can actually see that. So if you do want option 1, let me know. But cursed math. Commutative means that the order doesn't matter. So when you add 1 plus 2, that's the same thing as 2 plus 1, right? If you're adding up infinitely many numbers, that's no longer true. You cannot always rearrange sums. In an infinite series, you cannot always rearrange your terms and still get the same answer.
Wow.
I'm going to give you an example that shows you that this is true. And this involves the alternating harmonic series. You saw this in the lab. So alternating, short for alt, or shortened to alt. Negative 1 to the n plus 1 over n. So 1 minus half plus a third minus a fourth plus a fifth minus 6, so on and so forth. What I want to invite you to do is think about what happened if you could rearrange the series. I'm going to suggest one specific rearrangement. There are tons of these. This is a fun mathematical thing to do for certain values of fun. I'm going to group terms so that I do an odd term followed by 2 even terms. So 1 minus a half minus a fourth plus a third. What's the next even term? I've got negative 1/2, negative 1/4. What's the next even term? Negative 1/6. And the next one after that is negative 1/8. What's the next odd term? 1, a third. Yeah. All the odd terms are positive because that makes the negative 1 to the even thing. All the even terms are negative because that makes this negative 1 to an odd power. Is there a nice pattern you're noticing with these triplets that I've got here? What do they look like in general? These triplets look like 1 over an odd number. How do we write an odd number in general? Yeah. 2n plus 1 or 2k plus 1, pick your favorite variable. And then what do the two things that subtract from it look like? If I'm having odd thing, how are these two terms related in the pattern you're seeing? They're even. And what do they look like in relation to this odd number? This was 1, 2 and 4, 3, 6 and 8, 5, 10 and 12. Yeah, 2 times 2n plus 1. And what's the next one after that? It's the next even number. That's what your pattern looks like in general. We've got these triplets here. Now, what is this sum? If I take these fractions and I combine them, what do I get? No, why? Cursed. Oh, that happened. This was happening in this lecture hall like 3 years ago. There are some traditions that never change. This is the you've gotten too slightly after 7 o'clock surprise shutdown. Okay. Please focus. Hi. Not my hands. Down here. You can do it. Come on. There we go. Okay. Yeah. Okay, so this is just lowercase a algebra, so we can do it. It might hurt us, but we can do it. If you have this minus this, what's the difference between these two terms? This is just 1 over, I have thing minus half of the thing, so I just get like, I just get this, right? People okay with this? I have thing minus half of thing. That leaves me with half of the thing. Yeah. If you go back to our green sum, what does this look like? I have 1 minus a half, so I've got a half minus a fourth. I've got a third minus a sixth, so I get a 6 minus an eighth. I've got a 5 minus a tenth, so I've got a tenth minus a 12th. What is this series? What have I wrote down here? If I have a half minus a fourth plus a 6th minus 8th plus a 10th minus a 12th, what is another way to describe this? If I pull out a half, what do I get? 1 minus half plus a third minus a fourth plus a fifth minus 6 plus 7 minus an eighth. So this is half of our original series. So I took my thing and I rearranged it and I got half of my thing. So what numbers do this? What numbers are equal to half of themselves? Yes, the only number that is equal to itself when I divide it by 2 is going to be 0. If this is equal to half of itself, the only thing you divide by half and not change it is if it's 0. But can this be 0? If I take 1 minus a half, and a third minus a fourth, and a fifth minus a sixth, am I going to get 0? Why can't I get 0? First term is bigger than the second term, but that could maybe change later on. But what happens as I keep going through this? If I group these terms in pairs, I get a half, I get a 12th, I get a 30th, 1 times 2, 3 times 4, 5 times 6, I get 7 times 8th. Is this going to be 0 if I add up a bunch of positive numbers?
No.
So this is not 0. And so what have we learned? We have learned you cannot rearrange series. When you do rearrange them, bad things can happen.
Can you bring that one page to front?
And that's really weird, because you should be able to rearrange addition. 1 plus 2 is 2 plus 1. But if you're doing something to infinity, that stops being true. Yes?
Why does it do that?
What's up?
Why not? Why?
So here's the moral picture. If you want rigorous proofs, there's epsilon delta language here.
Wait.
Yeah, here's like a moral picture of what's going on here. You can make this more rigorous epsilons and deltas. If you want to know how to do that, write me, contact me. I love this stuff. But roughly speaking, what's happening is the following. When you take a series and you're talking about what it converges to, you're saying, I have my partial sums. I just take my terms. I keep adding them up. I want to know where they go. Most of the time, for most of the series you've dealt with in this class, you actually can rearrange them and you won't get into trouble. Most rearrangements will be fine. But the alternating harmonic series does something weird. On one hand, if you look at the even terms, you have negative a half, negative fourth, negative a sixth. That's a negative copy of half of the harmonic series. And the harmonic series went to infinity, right? So if I multiply it by negative a half, it's still going to go to infinity. Negative half infinity is negative infinity. But if I look at the odd terms, I've got 1, a third, a fifth, a seventh. I can bound that below by a half, a fourth, a sixth, an eighth. That's bigger than half of a harmonic series, which again will diverge to infinity. So this alternating harmonic series contains in its positive terms something that wants to go off to infinity, and its negative terms something that wants to go off to negative infinity. And when you add them together like this balanced form like this, you're saying we're going to alternate this thing that wants to go off to positive infinity, this thing that wants to go off to negative infinity in a very delicate, careful way. And you can turn out, if you can do a bit of calculus, it's in the course book. This will actually go to natural log of 2. You can prove this by using integrals. It's very neat. But if you have something that wants to go off to positive infinity and something wants to go off to negative infinity, you could cheat a little bit by taking that bit that goes to positive infinity and like adding up a bunch of those terms until it converges to something you want. Maybe it gets to bigger than 80, for example. Then add a few of those negative terms until you get below negative, until you get below 80. And that'll happen because the negative terms go off to negative infinity. So if you add a bunch of those, you eventually wind up going below it. Now take the positive terms, start adding them up again. That wants to go off to infinity. So it doesn't matter where you start, it's still going to go off to infinity if you wait long enough. So eventually go up above that thing you want. Now add some negative terms until it goes below, above, below, above, below. If you do this, you can make it converge to anything you want. Because if you alternate your positive and negative things, both of which want to go off to infinity in opposite directions, you can shape it to do any behavior you want. And as a result, you're not going to get a consistent answer. Making that rigorous is like the point of Maths 130 and then Maths 253 and then Maths 332 in sequence. But also, if you just like grab a copy of a good calculus textbook and spend a week staring at it until your brain comes out of your head, you can also do it right now. So that's cool.
Is this like if you do some rearranging of the sum of the natural numbers in the end as well?
No, that's a different cursed thing. So that's Ramanujan's summation, and that's basically the notion of summation we've got here is one way you can talk about the limit of these sequences. Another way you could talk about it is, on average, what do the sums go to? If you're doing something like that, then you have 1, like -1 plus 1 minus 1, that alternating between 1 and 0. You could say that morally it kind of goes to a half because it sums alternating between 1 and 0. And that is a worse definition of series convergence. Well, not worse. It's just different. It does a lot of cool things. But that's the kind of different notions of series convergence you need to do Ramanujan summation. But if you look at Ramanujan summation on Wikipedia, Ramanujan, Ramanujan. Do people know who Ramanujan was? He's legitimately, he's cool. His story is very tragic. There are many tragic math stories, like between him and Galois. Galois got a good tragic story. And then in cryptography, Alan Turing. So if you want to pick your 3 tragic mathematicians, those are a good trio. But if you don't know who Ramanujan is, look him up. He's cool. He's got a cool story. Anything else? People happy? Okay. That is lecture for the day. If you got questions, come talk to me. Otherwise, that is what we want.